The Cascadia subduction zone has been silent for more than 300 years, but silence does not always mean safety. A recent earthquake has drawn expert attention because it occurred near a fault capable of producing one of the largest earthquake and tsunami events in North America. In this video, the evidence is followed layer by layer. Please like, subscribe, and stay with the channel for more quiet documentaries about the hidden forces shaping Earth. The Pacific Northwest rests beneath long bands of cloud, forest, rain, and cold ocean air. Along the outer edge of North America, the land curves from Northern California through Oregon and Washington toward Vancouver Island and the coast of British Columbia. Mountains stand inland behind dark evergreen forests. Rivers move slowly toward the Pacific Ocean through broad valleys shaped by ice, floodwater, and ancient volcanic rock. Fishing harbors sit beside sheltered inlets. Small coastal towns face long beaches where winter storms arrive from distant parts of the ocean. Farther inland, large cities spread across lowland basins where millions of people live above layers of sediment and glacial soil. At first glance, the region appears quiet and stable. Beneath this calm surface, however, scientists observe one of the most closely watched earthquake regions on Earth. The Cascadia subduction zone stretches for roughly 1,000 kilometers along the offshore margin of the Pacific Northwest. A subduction zone is a place where one tectonic plate moves beneath another and sinks slowly into Earth's interior. In Cascadia, the small Juan de Fuca plate moves beneath the much larger North American plate. The movement is extremely slow, only a few centimeters each year. Yet the forces involved are immense because the plates are made of rigid rock extending across vast distances. The coastline itself gives few immediate signs of this movement during ordinary years. Tides rise and fall. Rain moves across cedar forests. Fishing boats leave harbour before sunrise. Waves erase tracks in wet sand. Daily life continues across cities, farms, islands, and mountain valleys. Unlike parts of California or Japan, the Pacific Northwest experiences relatively few large earthquakes close to the surface. Many residents pass years without feeling noticeable shaking. This absence of frequent destructive earthquakes creates an impression of safety that remains deeply rooted in the public memory of the region. Scientists approach this quiet with caution rather than comfort. Earthquake records from the past century show that Cascadia behaves differently from many active fault systems. In regions where tectonic strain releases more often, smaller earthquakes can occur frequently enough to reveal where pressure is building. Cascadia remains comparatively silent. Seismologists use the term seismic gap to describe a long fault region with unusually low earthquake activity compared with surrounding areas. The silence itself becomes important evidence. Modern instruments spread across the Pacific Northwest continuously measure movement in the ground. Sensitive receivers connected to satellites detect motions smaller than the width of a fingernail. These measurements reveal that parts of the coastal region are slowly deforming. In some places, the land compresses horizontally. In other places, it rises slightly over time. These motions occur so gradually that human senses cannot detect them directly. Only long observation through instruments reveals the pattern. The data indicate that tectonic strain continues to accumulate beneath the region, despite the outward calm. The concern among researchers does not arise from one recent earthquake alone. Instead, it grows from the combination of several observations gathered over decades. Small offshore earthquakes, unusual tremor patterns, new imaging of the deep crust, and refined measurements of plate motion together. suggest that Cascadia remains active in ways that are not always visible at the surface. Recent seismic events attract attention because they occur within this broader scientific context. Each earthquake provides new information about stress, fault geometry, and movement beneath the coastline. The Pacific Ocean west of Cascadia also shapes the character of the region. Storm systems generated over thousands of kilometers of open water strike the coast through much of the year. Heavy surf erodes cliffs and beaches. Thick marine sediments settle offshore in deep basins. Cold currents support rich marine ecosystems. From the shoreline, the ocean appears endless. Yet beneath its surface lies a complex landscape of ridges, canyons, buried faults, and volcanic structures formed over millions of years. Much of the tectonic boundary itself remains hidden below dark water. This hidden setting contributes to scientific uncertainty. Land-based earthquake faults can often be mapped directly through visible fractures, displaced rock layers, or surface breaks. Cascadia's main plate boundary lies mostly offshore and underground. Researchers rely on networks of ocean sensors, ship surveys, seismic imaging, and indirect measurements to understand its behavior. Each method provides only part of the larger picture. Observations indicate ongoing strain accumulation along portions of the fault. It remains uncertain exactly how stress distributes itself across the entire boundary at any given moment. Historical memory in the Pacific Northwest also differs from regions with repeated destructive earthquakes. The last full-margin Cascadia megathrust earthquake occurs in the year 1700. A megathrust earthquake is an extremely large rupture along a subduction boundary. The event takes place before modern scientific instruments exist in North America. No written local records survive from indigenous communities. Though oral traditions in several coastal nations describe violent Sheikh-near floods and great ocean waves, evidence from Japan records an orphan tsunami, meaning a tsunami arriving without a locally felt earthquake, crossing the Pacific Ocean in the winter of that same year. Geological studies later connect these observations to Cascadia. More than 3 centuries pass afterward without another known full-margin rupture. In geological terms, this interval remains relatively short. In human terms, it spans many generations. Cities grow, ports expand, roads, bridges, dams, pipelines, and electrical systems spread across the region. Dense urban corridors emerge around Seattle, Portland, and Vancouver. The quiet landscape becomes increasingly populated while the tectonic system beneath it continues its slow motion. Experts remain attentive because long periods without major earthquakes do not remove tectonic forces. In some cases, silence can reflect a locked fault where stress accumulates steadily over centuries. Cascadia's reputation among Earth scientists emerges from this combination of rare but potentially immense earthquakes, limited historical experience, and persistent geological evidence of active strain. The region appears calm at the surface while deep mechanical processes continue far below the forests, rivers, cities, and coastal waters of the Pacific Northwest. The coastal margin of Cascadia forms a narrow meeting place between land, sea, river sediment, forest soil, and slow vertical motion. It is not a single straight line. It bends around capes, estuaries, tidal flats, river mouths, barrier beaches, rocky points, and long bays where saltwater moves inland with each tide. Along this edge, the land appears low and quiet in many places. Marsh grasses grow in sheltered wetlands. Spruce and cedar stand near the high tide line. Sand dunes shift under wind. Mud settles in still water behind spits and islands. The surface seems soft, but it preserves a record of sudden change. Many of Cascadia's strongest clues about past great earthquakes come from these coastal wetlands. In ordinary years, tidal marshes rise and sink slowly as sediment gathers. Plants grow and sea level changes. Their soils form in thin layers. Dark bands of peat develop where plants live in fresh or brackish marshes. Lighter layers of sand and mud arrive during floods, storms, or waves. When conditions remain steady, each layer rests gently on the one below it. When the land suddenly drops, the environment changes quickly. A forest or marsh that once stands above regular tides can sink low enough for salt water to cover it. Researchers find evidence of such sudden sinking along many parts of the Cascadia coast. Buried soils appear below present tidal flats. Rooted stumps stand in growth position beneath younger mud. These are often called ghost forests, not because they are mysterious, but because they are the remains of trees killed when the ground drops and salt water enters their roots. The trees do not fall first. They die while standing. Their trunks and roots remain fixed in place, showing that the land itself moves downward rather than the trees being carried in from somewhere else. The drowned forests provide one of the clearest surface records of Cascadia's earthquake history. Tree rings can be measured in the dead wood, and the outermost preserved rings can show when growth stops. In several places, studies find trees that die close to the winter of the year 1700. This timing agrees with the tsunami record across the Pacific Ocean and with coastal subsidence records along North America. Observations indicate that a very large earthquake causes parts of the coast to drop suddenly. It remains uncertain how every small section of the coast moves during each ancient event, because the amount of sinking can vary from place to place. The pattern of coastal change is not uniform. Some marshes show repeated buried soils separated by layers of tidal mud. Each buried soil marks a former land surface. Each overlying mud layer shows that the surface becomes lower relative to the sea over long periods. This creates a stacked record of repeated sudden drops. The record is delicate. Storms, river floods, erosion, and local sediment supply can disturb or hide parts of it. Scientists compare many sites along the coast to separate earthquake signals from ordinary coastal processes. At some estuaries, a thin sheet of sand lies above buried marsh soil. This sand can be left by a tsunami, a long ocean wave caused by sudden movement of the seafloor. When a great subduction earthquake lifts or lowers parts of the ocean floor, it can push seawater into motion. The wave reaches shore and carries marine sand inland over marshes, tidal flats, and low forest floors. After the water drains away, a sand layer can remain. These sheets are often only a few centimeters thick, and they may be patchy, but their position above suddenly drowned soil strengthens the evidence for an earthquake and tsunami occurring together. The coastal record carries both precision and uncertainty. Some places preserve clear layers with strong dating evidence. Other places preserve incomplete traces. Radiocarbon dating can narrow the age of organic material, but it often gives a range rather than an exact year. Tree ring evidence can sometimes provide sharper timing when preserved wood is available. Sand sheets can show that a strong wave entered an area, but their absence does not prove that no wave came, because later erosion or lack of sand can remove the evidence. Scientists build confidence by looking for agreement among many kinds of observations. The recent attention around Cascadia fits into this wider coastal record. A modern earthquake near the region may be small compared with the great rupture of the year 1700, but it draws expert interest because the coast already shows that the fault can move suddenly and broadly. The present landscape is therefore not judged only by current quiet. It is judged by repeated traces of land level change stored in marshes, forests, and estuary sediments. The coast becomes a slow archive of events that no instrument recorded. Human settlement now occupies many of these same low areas. Roads cross tidal flats, houses stand near estuaries, ports and marinas sit close to sea level. Bridges connect islands and river mouths. Treatment plants, electrical substations, fuel storage sites, and communication lines often lie in flat coastal ground because such ground is easier to build upon. These places also tend to be exposed to subsidence and tsunami flooding. The scientific concern does not come from alarm. It comes from the simple overlap between known geological processes and modern infrastructure. The coastal margin also records gradual motion between great events. Instruments show that some areas rise slowly as the locked offshore fault bends the edge of the continent upward. During a major rupture, some of that stored bend can relax, and the coast can drop. This cycle is simplified, and the real pattern is more complex, but it helps explain why a coast can appear stable for generations and then change within minutes. The marshes preserve the result in layers of peat, mud, sand, and dead roots. Along Cascadia, the outer land is therefore a place of quiet evidence. It does not announce strain with constant shaking. It holds the signs in wet soils, drowned trees, tidal channels, and thin sand sheets. The recent earthquake has experts attentive because it occurs beside a coastline that already bears the marks of rare, large, and sudden movement. The surface remains calm in ordinary weather, yet the land itself records that calm as temporary within a much longer geological rhythm. Beyond the beaches, estuaries, and drowned forest soils, the Cascadia margin continues beneath the Pacific Ocean as a broad and uneven seafloor. This offshore region is hidden from ordinary sight, yet it carries the main shape of the plate boundary. From the coast, the ocean surface may look like a single moving plane of waves, wind, foam, and grey light. Beneath it, the bottom descends across a continental shelf, bends down a continental slope, and reaches deeper basins where sediment gathers in thick layers. The seafloor is not smooth. It holds channels, ridges, buried scarps, folded beds, volcanic rocks, and long zones where the crust has been squeezed, scraped, and broken. The continental shelf along Cascadia varies in width. In some areas it extends far from shore before the seafloor steepens. In other areas it narrows near capes and submarine canyons. Rivers bring sand, silt, clay, and organic matter from the mountains and lowlands to the sea. Storm waves and currents move this material across the shelf. Over time, the sediment becomes part of the offshore archive. Some layers settle slowly from quiet water. Some arrive quickly during floods. Some move downslope in dense underwater flows called turbidity currents. A turbidity current is a moving cloud of water and sediment that travels along the seafloor, often through submarine canyons. Its deposits can preserve evidence of strong shaking when underwater slopes fail during earthquakes. The outer shelf and slope lie above a zone where the incoming oceanic plate begins to pass beneath the continent. Before the plate fully descends, material on its surface is partly scraped off and added to the edge of North America. This scraped and folded mass is called an accretionary wedge. It forms from sediment, fractured rock, and material pushed together by plate convergence. In Cascadia, this wedge is wide and complex. It contains folds where layers bend under compression, thrust faults where one block of rock moves over another, and zones of weak sediment that deform slowly through time. Mapping this offshore landscape requires instruments because the water hides the structure. Ships send sound pulses downward and measure their return to build maps of seafloor depth. This method is called bathymetry. More detailed surveys use many sound beams at once, allowing researchers to see ridges, channels, scarps, and slope changes with finer clarity. Other surveys send controlled sound energy into the seafloor and record echoes from buried layers. This seismic reflection imaging helps reveal sediment layers, faults, and the shape of structures below the bottom. These methods do not show the fault as a simple line. They show a layered, bent, and fractured offshore margin shaped by long compression. The recent concern around Cascadia grows partly because the offshore region is difficult to monitor at the same level as land. On land, instruments can be installed, repaired, and connected to power and communication networks. Offshore, pressure, corrosion, distance, storms, and deep water make permanent monitoring harder. Ocean bottom seismometers and pressure sensors can record valuable data, but they are fewer than land stations and more expensive to deploy. Each new offshore measurement can therefore change scientific understanding by filling a gap in a place where the most important structures are located. The seafloor near Cascadia also shows evidence of repeated disturbance. Submarine canyons cut into the slope and channel sediment toward deep basins. When strong shaking affects the margin, unstable slopes can fail and send sediment flows downslope. These flows can leave layers that appear in several channels and basins over similar time intervals. Researchers study such deposits to understand the timing of past large earthquakes. The interpretation requires care because storms, floods, and local slope failures can also move sediment. Agreement across widely separated sites strengthens the case that a regional earthquake caused the deposits. Offshore faults do not all behave the same way. Some lie within the accretionary wedge, some cut through shallow sediments, some may connect to deeper parts of the plate boundary, while others may only deform the upper wedge. This matters because shallow offshore fault movement can affect the seafloor and influence tsunami generation. A fault that reaches close to the seabed can move water more directly than a deeper fault, whose motion is partly absorbed by overlying rock and sediment. Observations indicate that Cascadia contains many shallow structures capable of deforming the outer margin. It remains uncertain how each structure participates during different earthquake sizes. The shape of the seafloor also influences how tsunami waves travel toward land. Submarine ridges, banks, canyons, and shelves can focus, slow, bend, or spread long waves as they move into shallower water. This does not mean that every coastal place faces the same pattern during every event. Local bathymetry, the location of seafloor displacement, tide level, coastal shape, and harbour geometry all matter. Scientists use mapped seafloor data to improve models, but the offshore margin remains more detailed in some areas than in others. The accuracy of a model depends partly on how well the underwater landscape is known. Near the base of the slope, the incoming plate carries its own surface features toward the continent. It brings sediment, small faults, volcanic seamounts in some regions, and roughness formed as the oceanic crust moves away from its spreading ridge. As this uneven plate approaches the margin, it interacts with the overriding wedge. Rough areas may influence where stress concentrates, where fluids move, and where small earthquakes occur. The exact role of this roughness is still studied. Because the plate boundary lies buried and direct observation remains limited, the offshore seafloor is therefore a working surface of the Cascadia system. It is shaped by compression from plate motion, loading by sediment, erosion by currents, and sudden disturbance during earthquakes. It records both slow and rapid processes. Recent earthquakes near the region draw attention because they occur beside this hidden terrain where many faults, folds, and sediment pathways meet. The surface of the ocean can return quickly to calm after wind and waves pass, but the bottom keeps a longer memory in bent layers, displaced sediments, and mapped scarps. In this offshore region, scientific caution comes from the combination of clear evidence and incomplete access. The seafloor shows that the margin is active and deformed. Surveys reveal structures that matter for shaking and tsunami hazard. Sediment records preserve traces of earlier strong motion. At the same time, water depth and distance limit direct measurement. Experts remain focused not because the ocean floor gives a single simple warning, but because it holds the buried geometry through which Cascadia's largest forces must eventually move. At the plate boundary, the offshore landscape becomes part of a larger movement that has continued for millions of years. The Juan de Fuca plate moves generally eastward and slightly northeastward toward the edge of North America. The North American plate moves more slowly over the same region, carrying the continent, the coastal mountains, the lowland basins, and the near-shore crust above it. Where these two plates meet, the denser oceanic plate begins to descend beneath the lighter continental edge. This meeting is not a clean seam between two flat surfaces. It is a broad contact between uneven bodies of rock, sediment, water, heat, and pressure. The Juan de Fuca plate is a remnant of a much larger oceanic plate that once covered a wider part of the northeastern Pacific. New oceanic crust still forms west of Cascadia along spreading ridges, where molten rock rises and cools as plates move apart. As this crust travels away from the ridge, it cools, thickens, and becomes denser. By the time it reaches the Cascadia margin, it is old enough and dense enough to sink into the mantle beneath North America. Its motion is slow by human standards, close to the growth rate of fingernails, yet the movement acts across a plate hundreds of kilometers wide. At the surface of the incoming plate, layers of marine sediment travel toward the continent. Some of this sediment enters the subduction zone, some is scraped off and added to the accretionary wedge, some is folded, faulted, and compacted as the plate boundary tightens. Water also enters the system through pores in the sediment and through cracks in the oceanic crust. This water matters because it affects friction, mineral reactions, and the strength of the rocks. Friction is the resistance that opposes sliding between surfaces. Along a subduction boundary, friction helps determine whether the plates slip smoothly or lock together for long periods before releasing suddenly. The contact between the Juan de Fuca plate and the North American plate is called the megathrust. A megathrust is the main fault surface of a subduction zone. It can extend from shallow offshore depths to deeper areas beneath the continent. In Cascadia, much of this surface lies out of direct reach. It is buried beneath sediment, crust, and ocean water. Researchers infer its shape from earthquakes, seismic imaging, gravity data, heat flow, geologic mapping, and measurements of ground motion. These methods show that the plate boundary dips gently beneath the coast and continues inland at greater depth. The direction and speed of plate convergence are central to understanding Cascadia. Convergence means the plates move toward each other. Where convergence is steady, strain must be handled in some way. If the boundary slides continuously, stress does not build as strongly. If the boundary is locked, the upper plate bends and shortens while the lower plate keeps pushing beneath it. Cascadia appears to include locked, transitional, and freely sliding regions. The exact distribution changes with depth, temperature, rock type, fluid pressure, and time. Observations indicate that a large part of the boundary can store strain. It remains uncertain how stress varies across every portion of the fault at any given moment. Plate boundaries also have edges and neighbours. North of Cascadia, the tectonic setting changes around Vancouver Island and the Queen Charlotte region. South of Cascadia, the system approaches Northern California, where the San Andreas Fault, the Mendocino Triple Junction, and other structures meet. A triple junction is a place where three plate boundaries come together. These neighbouring systems influence the overall stress field near the ends of Cascadia. The central portion remains defined by the subduction of the Juan de Fuca plate, while the ends connect into more complex zones of faulting and plate interaction. The recent earthquake that draws attention sits within this broader framework of plate motion. A single event may occur on a fault within the oceanic plate, within the overriding plate, or near the plate interface. Its meaning depends on its location, depth, focal mechanism, and relation to surrounding structures. A focal mechanism describes the style of fault movement that produces an earthquake. It helps scientists understand whether rocks move by compression, extension, or sideways shear. In Cascadia, even moderate earthquakes can matter scientifically because they illuminate parts of a system that is otherwise quiet. At the plate boundary itself, the rocks do not behave in one uniform way. Near the shallow offshore region, sediments may be weak, water-rich, and easily deformed. At greater depth, pressure increases and fluids may be squeezed from minerals and pores. Deeper still, higher temperatures change how minerals respond to stress. Some parts may creep, meaning they move slowly without producing large earthquakes. Other parts may remain stuck until stress exceeds frictional resistance. Between these behaviors, broad transition zones can produce slow slip and tremor. Slow slip is movement on a fault over days or weeks rather than seconds. Tremor is weak seismic vibration that often accompanies such motion. The main concern in Cascadia comes from the possibility that a large area of the megathrust can rupture in one great earthquake, or that large sections can rupture separately. Geological evidence shows that full margin and partial margin events have occurred in the past. The plate boundary is therefore not only a line of contact but a possible rupture surface stretching across a region larger than many countries. Its slow motion accumulates energy over centuries. When release occurs, the amount of shaking and seafloor movement depends on how much of the boundary slips, how far it slips, and how close that slip comes to the ocean floor. Still, the plate boundary does not provide a simple clock. Tectonic plates move steadily, but earthquakes do not follow a perfectly regular schedule. Some intervals between great earthquakes are shorter, others are longer. The geological record can estimate patterns, but it cannot identify an exact date for a future event. This uncertainty is part of the reason experts remain attentive after recent earthquakes. Each event becomes a small window into the stress and structure of the boundary. Not a prediction by itself. In the plate boundary region, Cascadia's quiet surface begins to connect with its deeper cores. The coast, the offshore wedge, the seafloor sediments, and the lowland cities all rest above a slow collision between oceanic and continental rock. The Juan de Fuca plate continues to move inward. The North American plate continues to resist, bend, and adjust. The recent earthquake has experts on edge because it occurs within a system where slow convergence, long silence, and clear evidence of past great rupture meet along one hidden fault surface. The locked zone of the Cascadia subduction zone is the part of the plate boundary where movement between the Juan de Fuca plate and the North American plate appears to be held back. The plates continue to converge, but instead of sliding freely past each other, portions of their contact remain stuck. This does not mean that the rocks are motionless. It means that the lower plate keeps moving inward, while the upper plate is dragged and bent by friction along the boundary. The motion is slow, broad, and mostly invisible at the surface, but modern instruments show its pattern across the coastal region. A locked fault stores strain. Strain is the change in shape that occurs when rock is pushed, pulled, or bent by force. In Cascadia, the edge of the continent is gradually compressed as the oceanic plate continues its descent. Some parts of the coast appear to move landward. Some areas rise slightly over years and decades. These motions are measured by satellite-based positioning instruments that can detect tiny changes in location. The measurements reveal that the land is not fixed. It is slowly deforming above the plate boundary. The locked zone is not a simple rectangle beneath the ocean. Its size, strength, and depth vary along the margin. Scientists describe coupling to explain how strongly the two plates are stuck together. A fully coupled section moves little or not at all on the fault surface while strain accumulates in the surrounding rock. A weakly coupled section allows more steady sliding. Coupling is inferred from surface motion, earthquake patterns, heat flow, and models of the underground fault. It cannot be observed directly over the entire boundary. Observations indicate strong coupling in parts of Cascadia. It remains uncertain how coupling changes at fine scale across the offshore fault. The upper edge of the locked zone lies offshore, where the plate boundary is shallow and hidden beneath sediment and seawater. This part is especially difficult to define because few instruments sit directly above it for long periods. If the shallow part is strongly locked, then a future rupture may reach close to the seafloor and move a larger amount of water. If the shallow part slips more smoothly, then some strain may be released without the same abrupt seafloor displacement. Evidence is mixed in places, and scientists continue to refine the picture. The uncertainty matters because small differences in shallow slip can strongly affect tsunami behavior. The lower edge of the locked zone lies deeper beneath the coast and inland areas, at greater depth. Rising temperature and pressure change the way rocks deform. Fault surfaces that are cold and brittle can remain stuck and break suddenly. Warmer rocks may deform more gradually. Between these behaviors lies a transition region where the fault may slip slowly at intervals. This transition can produce slow slip events and tremor without the violent shaking of ordinary earthquakes. These deeper motions show that the boundary is not silent everywhere. It moves in different ways depending on conditions. During the years between major earthquakes, a locked zone can make the landscape tilt slightly. The coast may rise while inland areas move differently. This bending stores elastic energy, like a slow flexing of rock on a continental scale. Elastic means that material can deform under force and partly recover its shape when the force is released. When a large earthquake ruptures the locked zone, the upper plate can rebound. Coastal areas that had been lifted may drop. Offshore areas may rise or shift. This sudden change is preserved in marsh records as buried soils and dead forests. The recent earthquake draws expert attention because any shaking near a locked plate boundary may help reveal how stress is arranged around it. A moderate earthquake does not by itself prove that a great earthquake is near. Most moderate earthquakes do not lead to larger ones. Still, in a region with a long quiet megathrust and clear evidence of stored strain, each event is examined carefully. Researchers look at its depth, its faulting style, its aftershocks, and its relation to known structures. They compare it with the expected location of locked, creeping, and transitional parts of the boundary. The locked zone also matters because Cascadia has not produced a major instrumentally recorded megathrust earthquake. Modern seismology has recorded large subduction earthquakes in other places, including Chile, Alaska, Japan, and Sumatra. These events show how locked zones can rupture over great distances and move the sea floor. They also show that each subduction zone has its own geometry, sediments, fluids, and rupture behavior. Cascadia shares the basic process of plate locking and release, but its exact behavior must be understood from its own measurements and geological record. Scientists use computer models to estimate the locked zone, but models depend on assumptions. A model may represent the fault as a surface with different patches of coupling. It may then calculate what pattern of land movement would result. Researchers compare the model with actual measurements from positioning stations. If the match is strong, the model becomes more plausible. If new data disagree, the model is adjusted. This process does not produce a single final answer. It produces a range of possible locked patterns that fit the evidence. The range narrows as observations improve. Offshore monitoring is one of the main limits. Land instruments can measure deformation well across coastal towns, islands, and inland basins, but the shallow locked zone lies beneath the ocean. Seafloor pressure sensors and acoustic positioning systems can measure vertical and horizontal movement offshore, but deployments remain sparse compared with land networks. Because the shallowest part of the fault has large importance for tsunami generation, this gap keeps scientific attention focused. The recent earthquake is viewed against this limited but growing offshore record. The locked zone is therefore a hidden region of held motion. It is not dramatic in ordinary time. It does not create constant shaking. It expresses itself through millimeters of annual ground movement, subtle coastal uplift, buried marsh layers, and rare earthquakes that show pieces of the stress field. Experts remain watchful because the same quiet that makes Cascadia feel stable may also reflect a fault surface resisting motion over centuries. The evidence does not give an exact date or a simple warning. It shows that a large part of the boundary is capable of storing strain, and the recent seismic activity occurs beside a region where stored motion remains one of the central concerns. Across Cascadia, strain patterns appear in motions too small and slow for ordinary perception. They are measured by instruments fixed to bedrock, buildings, monuments, and remote stations where antennas look upward toward navigation satellites. These stations record the steady position of the ground day after day, over years. The records show whether a place moves north, south, east, west, upward, or downward. The changes are often measured in millimeters each year, but when many stations are compared, they reveal a broad pattern of deformation along the Pacific Northwest. The coastal region does not move as a single rigid block. Some areas near the coast shift landward because the locked plate boundary drags the edge of North America toward the incoming oceanic plate. Farther inland, motions are shaped by wider North American plate movement, volcanic arc processes, basin structure, and older faults. The pattern is subtle but organized. The surface slowly records the balance between plate convergence and resistance along the buried megathrust. Where the fault is more strongly coupled, the upper plate may show stronger elastic bending. Where the fault slips more freely, surface motion may differ. Geodesy is the science of measuring the shape and motion of Earth. In Cascadia, geodesy helps connect the quiet surface to the hidden fault. Satellite positioning networks, tide gauges, leveling surveys, and seafloor instruments each contribute to the picture. A tide gauge measures sea level relative to land. so long records can show whether land is rising or sinking after accounting for ocean changes. Leveling surveys measure height differences across land routes. Satellite positioning provides continuous horizontal and vertical motion. Together, these methods help scientists separate local effects from regional tectonic deformation. The strain pattern is not constant everywhere along the margin. Northern Cascadia, Central Cascadia, and Southern Cascadia each show differences in the speed and direction of surface motion. Some of these differences may reflect the geometry of the subducting plate. Some may reflect variations in friction along the fault. Some may come from block rotation in the upper plate, where parts of the crust slowly turn or shear between larger tectonic boundaries. Observations indicate that strain accumulation is uneven. It remains uncertain how much of this unevenness reflects long-term structure and how much reflects changes during the current earthquake cycle. Recent earthquakes sharpen attention to these measurements because they occur within an already moving field. When an earthquake happens, instruments can detect sudden offsets if the event is large and close enough. They can also detect slower changes after the shaking stops. Afterslip is gradual movement on a fault following an earthquake. Post-seismic deformation is the broader ground motion that happens after an event as rocks and faults adjust. In Cascadia, even small changes are compared with the long-term background motion to see whether stress has shifted near important structures. The most direct strain measurements on land are strongest where station coverage is dense. Cities, research facilities, roads, and accessible coastal areas support many instruments. Remote forests, offshore islands, and high mountains have fewer stations. The offshore region remains the hardest part to measure. Because much of the locked fault lies beneath the ocean, scientists need seafloor geodesy to observe motion above it. These instruments may use acoustic signals between seafloor transponders and ships or autonomous platforms, or pressure records that show changes in depth. Such measurements are improving, but they are still sparse compared with land networks. This uneven coverage affects interpretation. A land-based station may record motion caused by locking offshore, but several different offshore locking patterns can produce similar motion on land. This is a common challenge in geophysics. The same surface signal can sometimes be explained by more than one underground arrangement. Scientists reduce this uncertainty by combining geodesy with seismic imaging, earthquake locations, heat flow, and geological evidence. The more independent observations agree, the stronger the interpretation becomes. Strain in Cascadia also changes through slow slip events. These events occur when part of the deeper plate boundary moves over days or weeks, rather than breaking suddenly in seconds. During slow slip, satellite positioning stations may record a temporary reversal or change in motion. The coast and inland areas shift slightly as the deeper fault releases part of its accumulated strain. These shifts are small, but they are clear in high-quality records. Slow slip often repeats at intervals in parts of Cascadia, especially beneath Vancouver Island, Washington, and Oregon. It shows that some regions of the plate boundary move episodically without producing damaging shaking. Slow slip does not remove the concern about the locked zone. It occurs mostly below or near the lower edge of the strongly locked region, where temperature and pressure allow a different style of fault motion. It may change stress around neighbouring areas, but its role in the timing of large earthquakes remains uncertain. Observations indicate that slow slip and tremor are part of Cascadia's normal behaviour. It remains uncertain exactly how they interact with shallower locked portions over centuries. Vertical motion is another important part of the strain field. Some coastal areas rise slowly during the interseismic period, which is the time between major earthquakes. This rise can be measured by satellite positioning, tide gauges, and comparisons of coastal landforms. During a great earthquake, some of this uplift may reverse as the coast subsides. The balance between slow uplift and sudden subsidence helps scientists understand where the upper plate is being bent. It also helps planners estimate how future land level changes may affect harbours, marshes, roads, and evacuation routes. Experts examine recent seismic activity against this background of measured deformation. A new earthquake may occur in a place where surface velocities suggest strong locking nearby, or it may occur in a region where the fault appears to creep more freely. It may align with known stress directions or reveal a local structure not previously clear. The event becomes one piece in a larger strain map. It is not interpreted alone, because isolated earthquakes can be misleading. Its meaning grows only when placed among years of ground motion, tremor aftershock patterns, and offshore structure. The strain patterns across Cascadia are therefore quiet measurements of stored movement. They do not speak through visible cracks or daily shaking. They appear as slow shifts in station coordinates, long tide gauge trends, repeated slow slip pulses, and small post-earthquake adjustments. The recent earthquake has experts attentive because it occurs within a region where the ground is already recording compression and bending. What is known is that the margin continues to deform under plate convergence. What remains uncertain is the exact distribution of locked and slipping patches beneath the ocean. The surface instruments keep measuring, and their steady records show that Cascadia's calm landscape is still in motion. Small earthquakes in Cascadia form a scattered pattern of brief movement within a much larger and quieter system. Many are too weak for people to feel. Some are recorded only by sensitive seismometers placed across the region. Others produce light shaking near the coast, beneath the ocean, or within inland crustal blocks. Each event begins when stress overcomes friction on a small patch of fault, causing rock to slip suddenly. The energy travels outward as seismic waves. Instruments record the arrival of these waves and allow scientists to locate the source, estimate the depth, and identify the style of motion. In a subduction setting, small earthquakes can occur in several different places. Some happen within the overriding North American plate, where old faults and crustal stresses remain active. Some happen within the descending Juan de Fuca plate as it bends, cracks, and changes under pressure. Some occur near the plate interface, where the two plates meet. Distinguishing among these settings matters because each one says something different about stress. A small earthquake within the oceanic plate may show internal bending or tearing. A small event on the plate interface may show direct movement along the boundary. A shallow crustal event may reveal stress in the upper plate rather than on the megathrust itself. Seismologists locate earthquakes by comparing the arrival times of different seismic waves at many stations. Fast waves arrive first, slower waves arrive after them. The time difference helps estimate distance from the station to the source. When many stations record the same event, the source can be placed in 3 dimensions. Better station coverage gives better locations. In Cascadia, land networks are strong, but offshore locations remain harder to resolve because many earthquakes occur beneath the ocean where stations are farther away. Ocean bottom seismometers improve this picture when deployed, yet long-term coverage remains uneven. The depth of a small earthquake is especially important. A shallow earthquake in the upper plate may affect a nearby town more strongly than a deeper event of the same size. A deep earthquake within the descending plate may be felt across a wider area, but usually does not directly reveal shallow locking. An event near the expected megathrust depth receives careful attention because it may help define the plate boundary. Still, depth estimates have uncertainty, especially offshore. Scientists often compare earthquake locations with imaging studies and known plate models before assigning meaning. The focal mechanism adds another layer of information. It shows the pattern of fault motion that produces the earthquake. Compression, extension, and sideways shear each create different wave patterns. In Cascadia, compressional mechanisms may indicate squeezing from plate convergence, while extensional mechanisms within the descending plate may indicate bending or internal stretching. Sideways motion may reflect regional shear or local fault geometry. The mechanism does not always identify the exact fault plane, because two possible planes can fit the same wave pattern. Researchers combine it with aftershock locations and mapped structures when possible. Small earthquakes also reveal clusters and lineations. A cluster is a group of events occurring near one another in space and time. A lineation is a narrow alignment that may follow a fault or structural boundary. Some clusters fade after days, some persist for months or years, some occur after a larger event as aftershocks, others appear as swarms, where many small earthquakes happen without one clearly dominant main event. Swarms can result from stress changes, fluid movement, or slow fault motion. In Cascadia, their interpretation depends strongly on depth and setting. Recent small earthquakes draw attention because they can outline parts of the fault system that are otherwise hidden. An offshore event may illuminate a branch fault in the accretionary wedge. A deeper event may mark the top or interior of the descending plate. A series of events may define a zone where stress is changing. These observations do not mean that a great earthquake is imminent. Most small earthquakes are ordinary expressions of a tectonic system. Their value lies in mapping stress and structure, not in acting as simple alarms. Cascadia also produces tremor, which differs from ordinary earthquake shaking. Tremor is a weak, extended vibration that lacks the sharp start of a typical earthquake. It often occurs near the deeper transition zone of the plate boundary and is commonly associated with slow slip. Tremor can continue for minutes, hours, or longer as small patches slip gradually. It is usually not felt by people, but instruments detect it as a low, persistent signal. Because tremor occurs repeatedly in some regions, scientists use it to track deep fault movement over time. The relation between tremor and small earthquakes is complex. Ordinary earthquakes involve rapid rupture on a small fault patch. Tremor reflects many tiny, slow, or repeating motions in a transitional environment. Both provide information about stress, fluids, and fault strength. In Cascadia, tremor helps define where the plate boundary changes from locked behavior to deeper sliding. Small earthquakes help locate brittle structures above, within, and below that boundary. Together, they make the quiet subduction zone more visible. Fluids may influence some small earthquakes. Water carried down with sediment and oceanic crust can be released as pressure and temperature increase. Fluid pressure can reduce effective friction on faults by partly supporting the weight of overlying rock. When fluid pressure changes, it may help small faults slip. This does not mean that fluids alone cause earthquakes. Tectonic stress remains the main driver. Fluids can modify when and where small patches fail. Observations in subduction zones around the world support this role, though the details vary by region. Experts examine aftershock patterns following a recent earthquake to understand whether stress has moved onto nearby faults. Aftershocks usually occur as the crust adjusts to a sudden slip. Their number and size tend to decrease with time. Their distribution can reveal the shape of the ruptured patch and surrounding structures. If aftershocks deepen, spread, or align with known faults, researchers compare them with previous events and regional stress models. The process is careful and measured, because early earthquake locations can change as more data are processed. Small earthquakes can also improve seismic hazard models by revealing which faults are active. A fault with no surface expression may still produce repeated small events. A mapped fault may be quiet for long periods. Earthquake catalogues, which are records of event times, locations, depths, and sizes, help scientists see patterns over decades. New instruments can detect smaller events than older networks, so catalogue completeness changes through time. Researchers account for these changes when comparing past and present activity. Within Cascadia, the importance of small earthquakes lies in their context. The region's largest hazard comes from the megathrust and from strong crustal or intraslab earthquakes that can occur within the overriding or descending plates. Small events do not release enough energy to reduce that hazard in a meaningful way. A small earthquake releases only a tiny fraction of the strain that a great subduction earthquake can release. Instead, small earthquakes serve as probes. They show where brittle failure is happening, where stress is concentrated, and where the hidden geometry may differ from earlier models. The recent earthquake has experts on edge in this measured scientific sense. It adds information to a system known for long quiet intervals and large past ruptures. It may clarify stress in one part of the offshore or coastal structure. It may show how the descending plate bends, how the upper plate responds, or how faults near the interface are arranged. What is known is that small earthquakes trace active pieces of the Cascadia system. What remains uncertain is how any single event relates to the timing of a future large rupture. The instruments continue to record faint signals, and those signals help turn the silent margin into a map of hidden motion. Cascadia does not behave as one even stripped from north to south. The subduction zone extends along a long margin, and each part carries its own shape, temperature, sediment thickness, plate motion, and fault structure. The same broad process continues throughout the region, with oceanic crust moving beneath the continent, but the details change along the way. These changes matter because earthquakes do not rupture through abstract lines on a map. They move through real rock. And real rock varies from place to place. In northern Cascadia, near Vancouver Island and the coast of British Columbia, the plate boundary lies within a setting shaped by strong curvature, island crust, and nearby transform motion farther north. A transform boundary is a place where plates slide mostly sideways past one another. The northern end of the Cascadia system meets a broader region, where plate motions change direction, and where the crust contains older structures inherited from earlier tectonic events. The result is a margin with complex stress patterns. Earthquakes in and around Vancouver Island can reflect subduction, crustal faulting, and motion in the descending plate. This northern region also has strong records of slow slip and tremor. Deep beneath Vancouver Island and nearby areas, parts of the plate boundary move in repeated slow events. These movements occur over days or weeks and are detected by ground motion instruments and tremor signals. They show that the deeper fault is active, even when damaging shaking is absent. The shallow locked region above remains a separate concern. The presence of slow slip does not mean that the shallow boundary is safe. It means that the deeper part of the system has its own way of releasing strain. Farther south, along Washington, the margin lies beneath a broad forearc region. A forearc is the part of the overriding plate between the ocean trench and the volcanic arc. In Washington, this region includes coastal lowlands, the Olympic Peninsula, Puget Sound, and sedimentary basins that can amplify shaking. The Olympic Mountains rise as part of the long history of compression, uplift, erosion, and accretion along the edge of the continent. The geography is varied, with islands, channels, basins, and mountain blocks. The plate boundary below this region has to be understood through both offshore data and land-based deformation. Washington also contains major population centers on soft ground. The scientific focus remains on the fault system, but the importance of segment differences becomes clearer when the same shaking source can affect different surface materials in different ways. Thick sedimentary basins can trap and strengthen seismic waves at certain frequencies. Bedrock ridges may respond differently from river valleys or artificial fill. This does not change the existence of the subduction zone, but it changes the way earthquake energy reaches communities. The northern and central parts of Cascadia therefore differ not only in deep structure, but also in the shallow materials that receive shaking. In central Cascadia, along much of Oregon, the offshore margin is shaped by thick sediments, broad shelves in some places, and a relatively continuous subduction system. The coastline includes long beaches, estuaries, forested headlands, and low communities near river mouths. Geological records from Oregon marshes show repeated sudden subsidence and tsunami sand layers. These records help identify past ruptures and compare them along the margin. Some events appear to affect broad areas, while others may affect only part of Cascadia. This distinction is central to the idea of segmentation. A segment is a portion of a fault that may rupture separately from other portions, or may join them in a larger event. Segment boundaries can arise from changes in fault geometry, roughness, temperature, sediment, fluids, or stress. They can also be temporary because a rupture may stop at a barrier during one earthquake and cross it during another. In Cascadia, scientists study whether northern, central, and southern portions have different rupture histories. The geological record suggests that some past earthquakes rupture much or all of the margin, while others may involve smaller sections. The exact boundaries of these sections remain uncertain. Southern Cascadia, near northern California and southern Oregon, approaches one of the most tectonically complex areas of western North America. Near Cape Mendocino, the Cascadia subduction zone meets the San Andreas system and the Mendocino fracture zone. This region contains frequent earthquakes compared with much of the rest of Cascadia. The crust is broken by interacting faults, and the plate motions shift from subduction to sideways movement. The southern end therefore releases stress in a more active seismic environment than the quieter central margin. The southern region also includes the Gorda Plate, a small and deformed part of the oceanic plate system related to the Juan de Fuca Plate. The Gorda Plate is internally strained and produces many earthquakes within the plate itself. These intraslab or intraplate events can occur offshore and beneath northern California. Their activity does not remove the possibility of megathrust rupture, but it shows that the southern system handles stress through several kinds of faulting. Experts pay attention to this region because earthquakes there can reveal how stress enters or leaves the Cascadia boundary near its end. Along the full margin, temperature varies with plate age, depth, sediment cover, and fluid movement. Temperature helps control whether a fault patch is brittle, transitional, or creeping. The incoming plate is younger and warmer than many subducting plates around the world, which may influence the depth range of locking and the distribution of slow slip. Sediment thickness also varies. Thick sediment can smooth parts of the plate boundary, change pore pressure, and affect how rupture moves. Rougher basement structures may create stronger patches or barriers. These possibilities remain active research topics. Segment differences also appear in coastal records. Some buried soils and tsunami deposits match across wide distances, supporting large events. Others appear more local or are preserved unevenly. Interpretation requires caution because absence of evidence at one site may reflect erosion, poor preservation, or lack of exposure. Scientists compare many records to identify patterns. They also use offshore turbidites, tree ring dating, radiocarbon ages, and Japanese tsunami record where available. The emerging picture is not random, but it is not perfectly simple. Recent earthquakes are examined through this north to south framework. An event near one segment may not say the same thing as an event near another. Its depth, location, and mechanism are compared with the local structure of that part of Cascadia. A northern event may relate to island margin complexity. A central event may clarify the quieter megathrust or upper plate faults. A southern event may reflect the more broken plate system near the triple junction. The same magnitude can carry different scientific meaning depending on where it occurs. The segmented nature of Cascadia keeps experts attentive because it prevents easy general statements. The margin is one connected subduction zone, but it is not uniform. It has sections that differ in structure, history, and present motion. What is known is that Cascadia has produced large earthquakes in the past and continues to accumulate strain along much of its length. What remains uncertain is how the next major rupture would choose its path through the varied northern, central, and southern regions. The fault is continuous enough to matter as a whole, and uneven enough to require careful attention to each part. Near Vancouver Island, the northern end of Cascadia becomes a place where the descending plate is not only bending beneath the continent, but also breaking into pieces along inherited boundaries. This region is shaped by the meeting of the Juan de Fuca Plate, the Explorer Plate, the North American Plate, and nearby transform motion farther north. The geometry is crowded and uneven. Plate edges curve, smaller fragments move at slightly different directions, and faults divide one piece of oceanic crust from another. Within this setting, recent imaging and earthquake studies indicate that part of the subducting plate system is tearing. A plate tear is a break or zone of separation within a descending slab. A slab is the part of an oceanic plate that has entered a subduction zone and is sinking into Earth's interior. The term does not mean an open empty crack like a split in dry ground. At depth, pressure is high and rocks remain pressed together. A tear instead describes a structural break where neighbouring parts of the plate move differently, deform differently, or become separated along a fault zone. Such tearing can occur where plate geometry changes abruptly, where one fragment continues to sink while another slows, or where a spreading ridge, transform fault, or plate boundary enters the subduction system. Off northern Vancouver Island, the Nootka Fault Zone separates the Explorer Plate from the Juan de Fuca Plate. This zone carries sideways motion and marks a major boundary between two oceanic plate pieces. As the plate system approaches North America, the two pieces do not enter the subduction zone in exactly the same way. Their motions, ages, temperatures, and shapes differ. Recent seismic imaging has revealed deep structural disruption beneath this area, with faults and earthquake alignments that suggest tearing within the descending plate. The evidence comes from sound waves sent through the crust, from earthquake locations, and from the style of fault movement recorded by seismic instruments. The tear matters because it changes the way stress can pass through the northern end of Cascadia. A continuous plate may transmit forces along a broad connected surface. A broken or tearing plate can concentrate stress near the break, alter the shape of the slab, and change how the plate boundary behaves nearby. This does not remove earthquake hazard. It also does not create a simple sign of an approaching earthquake. It shows that the northern part of the system is structurally complex and evolving. Observations indicate active deformation within the subducting plate near Vancouver Island. It remains uncertain how this deformation affects long-term rupture behavior on the main megathrust. Seismic reflection imaging helps reveal this hidden structure. In this method, controlled sound energy travels into the seafloor and reflects from boundaries between rock layers, faults, and changes in material properties. The returning signals are recorded and processed into cross-sections of the crust. In the Vancouver Island region, these images show disruptions that cut through sediments and oceanic crust, and in some interpretations extend toward the upper mantle. Earthquake catalogues show narrow alignments of small events near these structural breaks. Together, the images and earthquakes suggest that the plate is not descending as a single smooth sheet. The location of the tear is important. It lies near the northern part of the Cascadia margin, where the subduction zone interacts with the Explorer plate and nearby transform systems. This is not the central Oregon margin or the southern Gorda region. It is a distinct tectonic corner with its own geometry. The same discovery therefore should not be spread casually across the entire subduction zone. The northern tear helps explain local complexity near Vancouver Island, but it does not mean that the whole Cascadia subduction zone is shutting down. The broader margin still includes large locked sections, slow slip regions, and geological records of past great earthquakes. Public descriptions of a tearing plate can sound dramatic, but the scientific meaning is more careful. Subduction zones can begin, evolve, fragment, and eventually stop over millions of years. In the northern Cascadia setting, the tear may represent one part of a long process of reorganizing plate boundaries. The Explorer plate is small and tectonically complicated. Its interaction with the Juan de Fuca plate in North America differs from the more continuous subduction farther south. The tear may show how a subduction system decays at an edge, where a ridge or transform boundary approaches the trench. This process unfolds on geological time, not on the scale of ordinary news cycles. Small earthquakes around the tear help define where the slab is breaking. Their depths, alignments, and focal mechanisms show whether the crust is under compression, extension, or sideways shear. If earthquakes form a narrow band that matches a disrupted structure in seismic images, confidence increases that a real boundary exists. Still, the picture is incomplete. Earthquake locations have uncertainty, especially offshore. Seismic images depend on data coverage and interpretation. Different scientists may emphasize different parts of the same evidence. The strongest conclusion is that northern Cascadia contains a tearing or fragmenting slab structure near Vancouver Island. While the exact mechanical consequences remain under study, fluids may also move differently near a slab tear. Oceanic crust carries water in pores, fractures, and hydrated minerals. As the slab descends and warms, some of this water is released. A tear can provide pathways for fluids to move through or around the plate. Fluids can affect fault strength, melting processes, and earthquake patterns. In many subduction zones, slab edges and tears are associated with unusual seismicity and changes in volcanic or mantle processes. In Cascadia, the specific fluid pathways near the northern tear are not fully resolved. Observations suggest that the structure may influence deep circulation, but its detailed role remains uncertain. The tear also affects how scientists think about segmentation. A structural break within the descending plate could act as a barrier, a stress concentrator, or a boundary between different behaviors. During some earthquakes, rupture may stop near such a complexity. During others, rupture could pass through or around it depending on stress, friction, and fault conditions. No single observation can determine this for future events. Past earthquake records along the coast and offshore sediments must be compared with the deep structure to understand whether the northern margin has repeatedly behaved differently from areas farther south. For experts, the plate tear is important because it adds a sharper picture to a region that already stands out. The northern end of Cascadia has slow slip, tremor, complex plate boundaries, island crust, offshore faults, and now stronger evidence for fragmentation of the descending plate. These features do not all point in one simple direction. They show a system with several ways to store, transfer, and release stress. The recent earthquake gains attention when viewed inside this setting, because even a moderate event may illuminate how the broken slab and surrounding faults are responding to ongoing plate motion. In the plate tear region, the calm surface of the ocean hides a boundary that is not only sliding beneath a continent, but changing its shape as it goes. The rock is cold enough in places to break, warm enough in others to bend, and pressured enough everywhere to remain buried and compressed. What is known is that northern Cascadia contains evidence for a tear or tearing process in the subducting plate near Vancouver Island. What remains uncertain is how strongly that tear changes the size, path, or timing of future earthquakes. The discovery keeps experts attentive because it replaces a simpler image of a continuous slab with a more complicated structure at the edge of the subduction zone. Beneath northern Oregon, the descending plate lies closer to the surface than many earlier broad models once suggested. This shallow slab region is important because it changes how scientists understand the distance between the plate boundary, the coast, and the communities above it. The word slab refers to the oceanic plate after it begins to sink beneath the continent. In northern Oregon, newer seismic imaging, earthquake locations, and geophysical measurements indicate that the subducting Juan de Fuca plate may be shallower in some areas than older simplified maps showed. This does not change the existence of the Cascadia subduction zone. It refines the shape of one part of it. A shallow slab means that the surface of the descending plate is at smaller depth below the land or sea floor. Depth matters because it affects temperature, pressure, fault behavior, and the way seismic waves travel. A plate interface that lies closer to the surface may place locked or transitional parts of the megathrust nearer to coastal areas than expected. It may also influence where small earthquakes occur and how they are interpreted. In northern Oregon, the geometry is studied through seismic waves from earthquakes and from controlled sources, as well as through gravity, magnetic, and heat flow observations. Seismic waves travel at different speeds through different rocks. Cold, dense oceanic crust usually carries waves differently from warmer or more fractured continental material. By recording how waves move through the region, scientists build images of the hidden crust. These images are not photographs. They are models based on travel times, wave speeds, and reflections. When several methods point toward a similar shape, confidence increases. In the northern Oregon region, such studies suggest that the descending plate surface may rise gently beneath the margin and remain relatively shallow under parts of the forearc. The shallow slab region is not a flat plate beneath a flat continent. It bends, changes angle, and interacts with sediments and crustal blocks above it. Near the offshore margin, the plate boundary begins beneath thick sediment and accreted material. Moving landward, it descends under the coast and then beneath the forearc. The angle of descent may vary along strike, meaning along the length of the margin. It may also vary down dip, meaning in the direction the slab sinks. Small changes in dip can shift the location of the locked zone, the slow slip region, and the deeper tremor zone. Northern Oregon is a valuable area for studying this geometry because it lies near the central part of Cascadia, away from the more complex plate edges to the north and south. Even there, the structure is not simple. The margin contains accreted sediments, old volcanic rocks, basins, and faults inherited from earlier tectonic events. These materials affect how waves travel and how models are built. Scientists must distinguish the top of the oceanic plate from other boundaries that can reflect or refract seismic energy. This is one reason estimates improve gradually as data coverage expands. A shallower plate can influence thermal conditions. Temperature along the megathrust helps determine where rocks behave in a brittle way and where they begin to deform more gradually. If the slab is shallower, a given part of the interface may be cooler than if it were deeper, because it has not descended as far into warmer Earth materials. Cooler conditions can support brittle locking over a different depth range. This connection is not automatic, because fluids, sediment, mineral composition, and pressure also affect fault behavior. Observations indicate that geometry and temperature both matter. It remains uncertain exactly how these factors combine in every part of northern Oregon. The shallow slab also affects interpretations of small earthquakes. If an earthquake occurs at a certain depth beneath the coast, its relation to the plate boundary depends on where the boundary is expected to be. A revised slab model may place the event within the descending plate, within the overriding plate, or near the interface differently than an older model did. This can change the scientific meaning of the event. It may show internal deformation of the slab rather than movement on the megathrust, or it may suggest activity closer to the boundary than previously thought. Such distinctions are central when recent earthquakes are examined. Seismic hazard depends not only on earthquake size but also on source depth and distance. A shallower source can produce stronger shaking near the surface than a deeper source of the same size, though local ground conditions and rupture details also matter. For a megathrust earthquake, the position of the slipping area influences which coastal and inland regions experience the strongest shaking. It also affects how the seafloor moves and how tsunami waves begin. The shallow slab beneath northern Oregon therefore matters because it helps define where strong slip could occur, not because it gives a direct forecast. The Oregon coast preserves geological evidence of past subsidence and tsunami flooding. These records show that the plate boundary has produced large earthquakes, but they do not by themselves reveal the exact depth of the slab beneath each site. Geophysical imaging fills that gap. When coastal records and slab models are considered together, scientists can better estimate how the upper plate bends before earthquakes and rebounds during them. A shallower interface may change the expected pattern of uplift and subsidence along parts of the coast. The amount of change depends on the distribution of locking and slip. Uncertainty remains because offshore and onshore data have different strengths. Offshore surveys can image the outer margin and shallow fault structures. Land-based seismic networks record earthquakes and wave speeds beneath accessible areas. The region between them, near the coastline and beneath the continental shelf, is difficult to observe continuously. Models must bridge these spaces. Newer studies reduce uncertainty, but they do not remove it. The slab surface is mapped as a best estimate with ranges, not as a precisely known plane. Experts pay attention to the shallow slab because it makes the central Cascadia system more specific. Earlier broad views sometimes treated the subduction interface as a smooth surface, dipping steadily beneath the continent. Improved data show bends, variations, and local differences. Northern Oregon appears to contain a plate geometry that may place important parts of the interface at depths relevant to both earthquake rupture and surface shaking. This refinement matters for hazard planning. Building standards, evacuation modelling, and scientific interpretation of the recent seismic events. In the shallow slab region, the concern is measured and technical. The ground above does not need to show visible change for the underlying geometry to matter. The descending plate continues its slow motion beneath forests, rivers, towns, and coastal headlands. What is known is that newer observations support a more detailed and locally shallower view of the slab beneath northern Oregon. What remains uncertain is how this geometry controls the exact limits of future rupture and the pattern of shaking. The recent earthquake keeps experts attentive because it occurs within a system where improved images are revealing that the hidden plate boundary may lie closer and in a more varied shape than once assumed. Deeper along the Cascadia interface, the plate boundary passes into a region where pressure increases, temperature rises, and rock behavior changes gradually. The fault surface that begins offshore as a shallow contact between sediment-rich oceanic crust and the edge of the continent continues downward beneath the coast and inland forearc. In this deeper interface region, the rocks are still part of the same subduction system, but they no longer behave in exactly the same way as the colder, shallower portions above them. The boundary becomes a zone of changing strength, changing fluids, and changing styles of motion. Pressure grows with depth because more rock lies above the fault. This pressure presses the two sides of the boundary together. At the same time, fluids within pores and minerals can reduce the effective pressure on fault surfaces. Effective pressure is the part of the load that actually clamps rock grains together after fluid pressure is considered. Where fluid pressure is high, faults may slip more easily. Where fluid pressure is lower, contact between rock surfaces may be stronger. Along the deeper Cascadia interface, this balance is important because water carried down by the oceanic plate is gradually released. Temperature also rises with depth. Cold, brittle rocks near the shallow part of a fault can break suddenly when stress exceeds their strength. Warmer rocks can deform more gradually, especially over long periods. The deeper interface lies within this transition. It is not simply locked or simply sliding everywhere. Instead, it contains patches that may creep, patches that may slip slowly, and patches that may produce tremor. The change from brittle to more ductile behavior is gradual. Ductile means that rock deforms without breaking suddenly, especially under high temperature and pressure. Slow slip is one of the most important behaviors in this deeper region. During a slow slip event, part of the plate boundary moves over days or weeks rather than in seconds. The movement can release strain without producing damaging high-frequency shaking. Instruments on land detect small temporary shifts in position. Tremor often accompanies these events as a faint, extended seismic signal. In Cascadia, deep slow slip and tremor are observed beneath parts of Vancouver Island, Washington, and Oregon. Their repeated occurrence shows that the deeper interface is active even when the surface remains still. The deeper interface helps define the lower edge of the locked zone. Above it, the fault may store strain more strongly. Within it, the plate boundary may shift into transitional behavior. Below it, motion may become more continuous. The exact boundaries are not sharp lines. They depend on temperature, pressure, rock type, mineral reactions, and fluids. Scientists use tremor locations, slow slip patterns, earthquake depths, and heat flow models to estimate where this change occurs. Observations indicate that the deeper transition is broad and uneven. It remains uncertain how its details vary beneath every part of the margin. Fluids are central to this region. The descending Juan de Fuca plate carries water in ocean sediments, altered basalt, fractures, and hydrated minerals. As the slab sinks, increasing temperature and pressure drive chemical reactions that release some of this water. The fluids may move upward into the overlying plate, along faults, or through permeable layers. They can change fault strength and influence tremor. They can also contribute to melting farther inland. But within the deeper interface itself, their role is mainly mechanical and chemical. They help determine how rock surfaces hold, weaken, and slip. Earthquakes within or near the deeper interface tend to be smaller than the great megathrust events expected from the locked region, but they provide valuable information. Their depth and mechanism help identify where brittle failure still occurs. In some places, small earthquakes cluster near the top of the descending slab. In others, tremor dominates, and ordinary earthquakes are less common. This contrast shows that the deeper interface is not uniform. It contains neighboring areas where stress is released through different forms of motion. The recent earthquake is examined partly through this deeper framework when its depth places it near or below the expected megathrust contact. If it occurs within the descending slab, it may reflect bending, dehydration, or internal stress. If it occurs near the interface, it may mark a patch of brittle behavior inside a broader transition zone. If it occurs in the overriding plate, it may show how stress is transferred upward. The same surface shaking can therefore have different meanings depending on its true location. Accurate depth estimates become essential. At these depths, direct observation is impossible. No drill reaches the active deep Cascadia interface. Scientists rely on indirect methods. Seismic waves reveal contrasts in rock properties. Electrical conductivity studies can suggest zones where fluids are present, because fluids can allow electrical currents to pass more easily than dry rock. Heat flow measurements help estimate temperature. Satellite positioning records show surface movement during slow slip. Each method has limits, but together they form a consistent picture of a plate boundary changing behavior with depth. The deeper interface also influences the rhythm of stress transfer. Slow slip events may slightly increase or decrease stress on adjacent locked areas. The changes are small compared with the full strength of the megathrust, but they are scientifically important. Researchers study whether slow slip repeats with regularity, whether tremor patterns migrate along the margin, and whether any changes occur before or after ordinary earthquakes. Observations show interactions between different modes of fault slip. It remains uncertain whether these interactions can be used to anticipate large ruptures in a reliable way. This uncertainty is handled carefully. Slow slip and tremor are not treated as simple warnings. They occur repeatedly without causing major earthquakes. Their importance lies in showing that the fault is alive with motion below the locked zone. They help mark the region where the mechanical character of the boundary changes. They also provide natural experiments, because each slow slip event slightly loads and unloads nearby parts of the fault, while instruments record the response. The deeper interface is therefore a quiet transition layer in Cascadia's earthquake system. It lies below the more strongly locked region and above the warmer parts of the descending slab. It is shaped by pressure, heat, fluids, and changing rock strength. It moves through slow slip, tremor, small earthquakes, and steady creep. Experts remain attentive because this region connects the stored strain above with the more gradual motion below. What is known is that the deeper interface does not remain still. What remains uncertain is how its slow movements influence the timing and extent of future large ruptures. In the recent earthquake's context, the deeper boundary offers no simple prediction. but it adds essential information about how Cascadia shifts from locked silence into slow hidden motion. Above the descending Juan de Fuca plate, the mantle wedge forms a warm interior region between the sinking slab and the base of the North American plate. The mantle is the thick layer of earth beneath the crust, made of solid rock that can flow slowly over long periods. In a subduction zone, the wedge-shaped part of this mantle sits over the slab and beneath the volcanic arc. It is not molten as a whole. It is mostly solid, but under high temperature and long time. It can move like very thick material responding to force, heat, and changing chemistry. The mantle wedge in Cascadia is shaped by the slab below it. As the oceanic plate sinks, it carries water downward in sediments, altered volcanic rock, cracks, and minerals formed at the seafloor. With increasing pressure and temperature, these materials release fluids. The fluids rise into the overlying mantle wedge and change the melting conditions of the rock. Water lowers the temperature at which mantle minerals begin to melt. This can create small amounts of magma that later feed the Cascade volcanic arc. Within the mantle wedge, however, the important process is the exchange of water, heat, and rock strength. This region lies deeper than the locked part of the megathrust. It does not control coastal subsidence in the same direct way as the shallow fault interface. It affects the larger subduction system by influencing temperature, fluid pathways, and the mechanical state of the plate boundary above and around it. Heat from the mantle wedge helps set the thermal structure of the forearc and arc. The warmer the system becomes with depth, the more likely rocks are to deform gradually rather than break suddenly. This thermal pattern helps explain why the seismogenic zone, the part of a fault capable of producing ordinary earthquakes, is limited in depth. The mantle wedge is not the same everywhere along Cascadia. Temperature varies with the age and speed of the incoming plate, the depth of the slab, the thickness of the overriding crust, and the amount of fluid released. In some places, the wedge beneath the forearc may be relatively cool and strong. Farther inland beneath the volcanic arc, it is warmer and more chemically changed by slab-derived fluids. These differences appear in seismic wave speeds, electrical conductivity, heat flow, and volcanic activity. Observations indicate that fluids and temperature vary along the margin. It remains uncertain how finely these variations map onto fault behavior above. Seismic imaging helps scientists study the mantle wedge indirectly. Seismic waves tend to slow down in hotter, more fractured, or more fluid-rich rock. They move faster through colder and more rigid materials. By comparing wave speeds beneath Cascadia, researchers infer zones of cooler slab, warmer mantle, and possible fluid pathways. Electrical studies add another view. Rock containing interconnected fluids or small amounts of melt can conduct electricity more easily. High conductivity zones beneath parts of the arc and forearc may suggest fluids or melt, though the exact cause must be interpreted carefully. The mantle wedge also participates in slow circulation. As the slab descends, it drags nearby mantle downward. Warmer mantle from deeper or inland regions can flow into the wedge to replace it. This motion is extremely slow, measured over thousands to millions of years, but it helps transport heat. The circulation pattern is influenced by slab dip, plate speed, and the viscosity of mantle rock. Viscosity is resistance to flow. A more viscous mantle flows less easily, while a less viscous mantle can adjust more readily to moving plates. Fluid release from the slab changes minerals in the mantle wedge. Dry mantle rock is commonly dominated by minerals such as olivine and pyroxene. When water enters, it can form hydrated minerals, weaken rock, and alter its physical properties. Some reactions may store water temporarily, others may release it again at different depths. These reactions affect density, strength, wave speed, and melting. The system is therefore both mechanical and chemical. It is not only rock moving under force, but rock changing as water and heat pass through it. The Cascade volcanoes mark one surface expression of this deeper process. Mount Saint, Helens, Mount Rainier, Mount Hood, Mount Baker, Mount Jefferson, Mount Shasta, and other volcanic centers form because subduction releases fluids that help generate magma in the mantle and lower crust. The volcanoes are not directly caused by a recent earthquake in the ordinary sense. They are part of the same long-lived subduction system. Their existence shows that the slab is releasing fluids and that the mantle wedge is chemically active. Earthquake studies and volcanic studies therefore overlap in the deep interior, even when their immediate hazards differ. In the mantle wedge, stress is not released mainly through brittle earthquakes. The temperature and pressure are generally too high for widespread sudden brittle failure, though earthquakes can occur within the colder descending slab below. The wedge itself tends to deform slowly. This slow deformation influences the overlying plate by providing basal traction, heat, and pathways for fluids. The locked zone closer to the surface depends partly on the thermal and fluid conditions that the deeper system establishes. The link is indirect but important. Recent earthquakes in Cascadia are sometimes examined for any relation to deeper fluid or stress pathways, especially if they occur near the slab or beneath the forearc. Most individual earthquakes cannot be traced directly to mantle wedge processes. Their immediate cause is slip on a fault under stress. Still, the deeper environment helps create the conditions in which faults exist. If fluids rise along certain pathways, they may influence pore pressure above. If the slab geometry changes, mantle flow and heat distribution may also change. These links are studied cautiously, because the data are indirect and many explanations can fit limited observations. The mantle wedge also helps explain why Cascadia differs from colder subduction zones. The Juan de Fuca plate is relatively young compared with many oceanic plates that subduct elsewhere. Younger oceanic plates tend to be warmer and more buoyant. This affects slab angle, thermal structure, and dehydration depth. A warmer slab may release fluids differently and may limit the depth of brittle coupling along the interface. These broad tendencies are understood, but local details depend on real geometry, sediment, and rock composition. Cascadia's mantle wedge must therefore be studied as its own system, not only as an example of a general model. For experts, the mantle wedge is not the most visible part of the earthquake concern, but it is one of the deep controls. It sets heat, guides fluids, changes minerals, and allows slow rock flow above the slab. It connects the descending plate to the volcanic arc, and to the deeper transition from brittle faulting to ductile deformation. What is known is that water released from the slab alters the wedge and contributes to Cascadia's thermal and volcanic character. What remains uncertain is the detailed pattern of fluid movement and its exact influence on faults higher in the system. The recent earthquake keeps attention on Cascadia as a whole, while the mantle wedge shows that the system's quiet surface rests above a warm, slowly changing interior. Within the layers of sediment along the Cascadia margin, the earthquake record extends far beyond written history. This deeper memory is preserved in coastal marshes, offshore channels, submarine fans, lake beds, tree rings, and tsunami deposits. The record is not a single page. It is a set of separate natural archives that overlap imperfectly. Each archive forms in its own environment, responds to its own disturbances, and preserves evidence in its own way. Scientists compare them because no one archive contains the whole history. Together they show that Cascadia has produced repeated large earthquakes across thousands of years. Offshore turbidites are among the most important records. A turbidite is a layer of sediment deposited by a turbidity current, the dense underwater flow of water and sediment that moves downslope after sediment is disturbed. Strong earthquake shaking can trigger many submarine slope failures at nearly the same time along a wide margin. These failures send sediment through canyons and channels into deeper basins. When the flows slow, they leave graded layers, often with coarser material at the base and finer material above. If similar layers appear in several offshore channels at nearly the same age, they may indicate a regional earthquake rather than a local slope collapse. The Cascadia offshore record includes repeated turbidite sequences in deep-sea cores. Cores are long cylinders of sediment taken from the seafloor by research ships. They preserve layers in vertical order, with younger material above and older material below. Scientists examine grain size, chemistry, magnetic properties, microfossils, and radiocarbon ages from organic material. The goal is to identify layers likely caused by strong shaking and to compare them along the margin. Some sequences appear widespread, suggesting very large earthquakes. Others appear more limited, suggesting partial margin events or local disturbances. Interpreting turbidities requires caution. Submarine landslides can be triggered by earthquakes, but they can also occur due to rapid sediment loading, storms, floods, gas release, or slope instability. A single deposit in one basin cannot automatically be assigned to a great earthquake. The stronger argument comes from synchrony, where deposits of similar age occur across separate channels that are unlikely to fail together without regional shaking. Even then, dating uncertainty matters. Radiocarbon ages often have ranges, and sediment can contain older, reworked material. Researchers use many samples and statistical methods to narrow the timing. Coastal marsh records provide another line of evidence. Buried soils, dead tree roots, and sudden changes from freshwater or brackish marsh plants to tidal mud show that land level changed quickly. These changes fit the expected pattern of subsidence during great subduction earthquakes. Some buried soils are overlain by sand sheets carried inland by tsunamis. When a drowned soil and tsunami sand have similar ages, the evidence for earthquake-related subsidence strengthens. Along Cascadia, such sequences appear at many estuaries and tidal wetlands. They show repeated cycles of gradual marsh growth, sudden lowering, and renewed sediment accumulation. Tree ring evidence sharpens the most recent full margin event. In several coastal ghost forests, trees stopped growing in the late 17th century. The final preserved rings indicate death near the winter of the year 1700, across the Pacific Ocean. Japanese records describe an unusual tsunami arriving without a locally felt earthquake on a specific winter date in that year. These independent records fit together because a large Cascadia earthquake can generate a tsunami that crosses the ocean, while leaving no written European record from the Pacific Northwest. The agreement between trees, marshes, and distant tsunami history gives unusual precision to the last great event. Older events cannot usually be dated with the same precision. Radiocarbon dating of plant fragments, peat, shells, or charcoal gives age ranges that may span decades or longer. Some sites preserve many events clearly, others preserve only a few. Erosion can remove layers. Later channels can cut through older deposits. Tsunami sand may be absent where there is little sand available or where the wave does not leave a lasting layer. The record is therefore incomplete. but incompleteness does not erase the repeated pattern. Across many sites, the evidence points to multiple large Cascadia earthquakes during the Holocene, the present geological epoch that began after the last major ice age. The recurrence of Cascadia earthquakes is not perfectly regular. Geological estimates suggest intervals between major events vary widely. Some gaps are a few centuries, others are longer. This uneven timing is normal for large faults. Plate motion can be steady while rupture timing remains irregular because stress, friction, fluids, and fault interactions vary. The earthquake memory preserved in sediments therefore does not support a simple countdown. It supports the conclusion that large earthquakes have happened repeatedly and will remain part of the region's long-term tectonic behavior. The idea of full margin and partial margin rupture emerges from comparing records along the length of Cascadia. A full margin rupture affects much or all of the subduction zone from northern California toward Vancouver Island. A partial margin rupture affects a shorter section. Some offshore turbidite patterns and coastal records suggest that both types may have occurred. This interpretation remains debated in detail because preservation differs from place to place, and because dating uncertainty can blur the distinction between one long rupture and several closer events. Observations indicate variability in past rupture extent. It remains uncertain exactly how many events involved the full margin and where all partial ruptures began and ended. Lake records also contribute in some areas. Strong shaking can disturb lake sediments, causing underwater slides or mixed layers. If multiple lakes across a region show disturbance layers of the same age, they may support evidence for regional earthquakes. Lakes are useful because they can preserve fine annual or near-annual layers in quiet basins. They also have limitations. Storms, floods, and local slope failures can disturb lake beds. Scientists compare lake evidence with coastal and offshore records rather than using it alone. Indigenous oral traditions form another important part of the broader human memory, though they must be approached with respect and care. Several coastal nations preserve accounts of strong shaking, land changes, and destructive ocean waves. These traditions are not instrument records, but they carry knowledge of lived experience across generations. When considered alongside geological evidence, they align with the understanding that the Pacific Northwest coast has experienced great earthquake and tsunami events. Scientific work does not replace these traditions. It adds physical dating and process interpretation to a longer memory already held by people of the region. Recent earthquakes are viewed against this deep record. A modern event may be small compared with the largest prehistoric ruptures, but it occurs in a margin known to have repeated its largest behavior many times. Experts do not become attentive because one earthquake suddenly proves the hazard. They are attentive because the sedimentary memory already shows the hazard, and each new event adds detail to the present state of the system. The past record gives scale, frequency range, and rupture diversity. The present event gives a fresh measurement of stress release in one place. The earthquake memory of Cascadia is calm in its form. It is made of mud, peat, sand, wood, and fine layers settled in quiet water. It does not speak as a warning in ordinary time. It waits in river mouths, deep channels, marsh banks, and seafloor cores until researchers read it. What is known is that Cascadia has produced repeated large earthquakes and tsunamis over thousands of years. What remains uncertain is the exact timing, size, and length of the next major rupture. The record keeps experts on edge because it shows that the region's long quiet interval belongs to a much longer sequence of sudden motion, preserved one layer at a time. Hazard models for Cascadia bring many observations together into a careful estimate of future shaking, land level change, and tsunami flooding. A model is not a prediction of a date. It is a structured way to represent what is known about sources, ground motion, coastal shape, and uncertainty. In Cascadia, models draw from plate motion, fault geometry, geodetic strain, small earthquakes, slow slip, coastal subsidence records, offshore sediment layers, and examples from other subduction zones. Their purpose is practical as well as scientific. They help communities understand what kinds of effects are possible and where preparation needs to be strongest. The first part of a hazard model is the earthquake source. For Cascadia, this includes the megathrust, faults in the overriding plate, and earthquakes within the descending plate. The megathrust receives special attention because it can produce the largest events. Scientists represent it as a surface beneath the offshore margin and coast, with possible patches of different slip. Slip is the amount one side of a fault moves past the other during an earthquake. A model may test a full margin rupture, a northern rupture, a central rupture, a southern rupture, or several other patterns. Each pattern changes the distribution of shaking and seafloor movement. The amount of slip is another central choice. Large earthquakes do not move every part of a fault equally. Some areas may slip many meters, others may slip less. Slip may reach shallow parts of the fault near the seafloor, or it may remain deeper. These differences matter for both shaking and tsunami generation. Shallow offshore slip can lift or lower the seafloor more directly, setting more water in motion. Deeper slip may produce strong shaking over land while causing a different tsunami pattern. Observations from past subduction earthquakes around the world show that rupture can be highly uneven, so Cascadia models include a range of possible slip distributions. Ground shaking models estimate how seismic waves travel from the rupture into the surrounding region. The strength of shaking depends on earthquake size, rupture depth, distance, direction of rupture, rock properties, and local soils. Hard bedrock usually transmits waves differently from soft sediment. Basins can trap and amplify shaking. River valleys, artificial fill, and saturated ground may shake more strongly than nearby rock hills. In places such as Puget Sound, Portland Basin, Willamette Valley, and coastal lowlands, shallow geology can strongly affect what people and buildings experience. Liquefaction is one hazard included in many models. Liquefaction occurs when water-saturated sediment loses strength during shaking and behaves more like a fluid. It can damage roads, pipelines, bridge foundations, ports, and buildings, low-lying river deposits, artificial fill, and young sandy sediments are especially vulnerable. Cascadia's coastal towns, estuaries, and urban waterfronts contain many such materials. The hazard does not come only from the fault offshore. It also comes from the way local ground responds when waves arrive. Landslides are another modelled effect. Strong shaking can destabilize steep slopes in coastal bluffs, mountain valleys, road cuts, and river canyons. The Pacific Northwest has many slopes already weakened by rain, weathered rock, and past landslide deposits. During a large earthquake, some slopes may fail immediately, while others may become unstable and fail later during rainstorms. Models identify areas where slope angle, geology, moisture, and expected shaking combine to create higher risk. These maps carry uncertainty because individual slope failure depends on local conditions that can vary over short distances. Tsunami models begin with seafloor movement. When a megathrust earthquake displaces the ocean floor, the water above it is pushed upward or downward. The disturbance spreads as long waves across the ocean and toward the coast. In deep water, Tsunami waves may be low and fast. Near shore, they slow, grow, and interact with the shape of the seafloor and coastline. Cascadia's bays, harbours, river mouths, and estuaries can focus or modify incoming waves. A model uses bathymetry, coastal topography, tide conditions, and estimated seafloor deformation to calculate flooding zones. Tsunami modelling is especially sensitive to shallow fault behaviour. If the shallow megathrust slips strongly, seafloor displacement may be larger near the trench, and the first waves reaching the coast may be more severe in some areas. If slip remains deeper, the pattern changes. Because the shallow offshore fault is hard to observe directly, this remains a major source of uncertainty. New seafloor mapping, pressure sensors, and offshore geodesy help reduce the uncertainty, but they do not remove it. Models therefore present scenarios rather than a single outcome. Coastal subsidence is also included. During a Great Cascadia earthquake, some areas of the coast may drop relative to sea level. This can cause immediate flooding, change tidal reach, damage docks and drainage systems, and make tsunami effects worse in low areas. Geological records of buried marshes and ghost forests provide evidence for past subsidence. Geodetic measurements show present interseismic uplift in some places. Models combine these data to estimate where sudden lowering may occur. The exact pattern depends on which part of the fault slips and by how much. Recent observations can adjust hazard models in quiet but important ways. A newly recognized slab geometry may shift the expected depth of the interface. Better offshore bathymetry may change tsunami inundation lines. Improved ground motion data from small earthquakes may refine how waves pass through basins. Evidence for plate tearing or segment boundaries may influence which rupture scenarios receive more attention. None of these updates usually overturn the basic hazard, they refine it. Sometimes moving lines, changing probabilities, or identifying places where earlier assumptions were too simple. Probabilistic models handle uncertainty by considering many possible earthquakes and assigning likelihoods over a given time window. Scenario models describe a specific earthquake and its consequences without claiming that it is the most likely event. Both are useful. Probabilistic models guide building codes and long-term planning. Scenario models help emergency managers imagine concrete consequences for evacuation, transportation, hospitals, communications, and recovery in Cascadia. The most useful planning often comes from comparing several scenarios, because the next major event may not match any single example exactly. Experts remain careful about language. A recent earthquake may lead to detailed review, but hazard models do not usually change because of one small or moderate event alone. They change when new data improve understanding of fault geometry, strain accumulation, ground response, or past rupture history. The concern is cumulative. Cascadia's models become sharper as each observation fills part of the hidden system. A recent event matters when it helps test those models or reveals a structure that had been poorly known. The value of hazard modelling lies in its discipline. It accepts that the exact future earthquake is unknown, then describes a range of physically reasonable outcomes. It does not need certainty to be useful. It helps identify strong shaking zones, possible tsunami flooding, likely subsidence areas, unstable slopes, and vulnerable sediments. What is known is that Cascadia can produce damaging earthquakes and tsunamis, and that modern communities occupy ground exposed to those effects. What remains uncertain is the precise rupture pattern, slip distribution, and local response of the next large event. The recent earthquake keeps experts attentive because every new measurement can make the hazard picture a little less blurred, and in a quiet margin, Even small refinements matter. Scientific uncertainty in Cascadia begins with the simple fact that the most important fault surface lies mostly offshore, underground, and beyond direct human sight. The region is studied with increasing precision, yet no instrument can watch the entire megathrust at once. Researchers build understanding from many partial views. Satellites measure how the land moves. Seismometers record small earthquakes and tremor. Ships map the seafloor. Sediment cores preserve old disturbances. Coastal marshes record sudden sinking. Computer models test how these observations may fit together. The result is not ignorance. It is a detailed but incomplete picture of a large natural system. What is known is strong enough to shape expert concern. Cascadia is an active subduction zone. The Juan de Fuca Plate continues to move beneath North America. The coastal and inland ground continues to deform. Geological records show repeated large earthquakes and tsunamis over thousands of years. The last known full-margin event occurs in the year 1700. Modern cities, ports, roads, bridges, and coastal communities now occupy the region above and beside the fault. These facts are not speculative. They are supported by several independent lines of evidence that agree with one another. What remains uncertain is the exact state of stress along the fault today. Stress cannot be measured directly across the whole plate boundary. It must be inferred from motion, earthquakes, rock properties, and models. A section that appears locked may not be locked in the same way everywhere. A section that slips slowly at depth may interact with shallower locked parts in ways that are not fully understood. Offshore parts of the boundary remain less densely monitored than land areas. This means that the most important zone for tsunami generation also remains one of the hardest zones to measure continuously. The recent earthquake adds attention because it becomes another measurement inside this uncertain system. Its location, depth, fault motion, and aftershocks can refine the local picture. It may show stress within the descending plate, motion in the overriding plate, or activity near the interface. It may confirm known structures or reveal a hidden one. By itself, it does not provide a reliable forecast of a larger earthquake. Most earthquakes do not trigger great ruptures. The scientific value comes from context. In Cascadia, even moderate events are examined carefully because they occur within a margin capable of rare but very large motion. Experts are also cautious because earthquake timing remains irregular. Plate motion can be steady while earthquakes occur unevenly. The geological record shows that Cascadia does not rupture on a simple schedule. Some intervals between major events are shorter, others are longer. This prevents a precise countdown. It also prevents easy reassurance based only on the passage of time. A long quiet interval can mean that strain is accumulating, but it cannot state when release will occur. This is one of the central limits of earthquake science. Another uncertainty lies in rupture extent. The next large Cascadia earthquake may involve much of the margin, or it may involve a smaller section. It may produce strong, shallow slip offshore, or its largest movement may remain deeper. These differences would affect shaking, tsunami size, land subsidence, and damage patterns. Models can describe physically reasonable scenarios, but they cannot identify one future rupture in advance. The purpose of modeling is therefore not prediction. It is preparation across a range of possible outcomes. The uncertainty is not empty, it is bounded by evidence. The fault cannot behave in just any imagined way. Its geometry, plate motion, thermal structure, and past record limit what is plausible. Scientists know that great subduction earthquakes are possible because they have happened before. They know that the coast can sink because buried soils and ghost forest preserve that motion. They know that tsunamis can cross the Pacific because the year 1700 event left records far from its source. They know that the ground is deforming because instruments measure it. These observations hold the uncertainty within a real physical frame. The recent attention from experts therefore reflects discipline rather than alarm. It comes from watching a quiet margin with a powerful history, a hidden locked zone, uneven segments, deep slow slip, and newly refined images of the descending plate. Each new earthquake is not treated as a signal with one meaning. It is treated as data. It is compared with previous events, with plate models, with offshore maps, with tremor, with ground motion, and with geological evidence. The process is slow, careful, and cumulative. Cascadia remains a place where the surface can seem peaceful while deep motion continues. Forests stand over bending crust, estuaries cover buried soils, cities rest on basins that remember ice, rivers, and sediment, offshore. The plate boundary lies beneath cold water and layered mud. Deeper still, the slab descends through pressure, heat, and fluids. The system does not need constant shaking to remain active. Its motion is measured in long records, faint tremor, scattered earthquakes, and the quiet tilt of the land. What experts know is enough to keep attention steady. What they do not know is enough to keep research active. The recent earthquake matters because it enters this balance between evidence and uncertainty. It does not close the question of Cascadia's future. It sharpens one part of the present. In a region where the largest events are rare, every accurate measurement helps. The margin is watched not because certainty has arrived, but because the combination of known hazard, incomplete offshore data, and modern exposure makes careful observation necessary. The account grows quieter here, returning from the deep fault to the surface where rain moves across roofs, forests, roads, and dark water. Cascadia remains a region of ordinary days above extraordinary geology. The plates continue their slow motion without haste. Instruments keep their steady watch. Marshes keep their layered memory. The ocean covers the long boundary where rock presses against rock in darkness. No single recent earthquake explains the whole system. It becomes one measured event among many forms of evidence. The science remains careful because the Earth gives partial signs, not complete statements. Observations show that strain accumulates, that the coast has shifted before, and that the hidden boundary can produce great rupture. Observations also leave uncertainty about timing, extent, and exact motion. This is the calm truth at the center of the concern. The surface does not need to change for the process to continue. Trees grow, rivers carry sediment, waves cross the shelf, satellites mark small movements year after year. Seismometers record faint vibrations that pass through stone and fade. Beneath them, the plate boundary remains part of a longer rhythm than human memory can easily hold. The story settles into that slow scale. A recent earthquake draws expert attention because it touches a system already known to be active, complex, and unfinished in its scientific details. The attention is steady, not frantic. It is the attention given to a quiet margin with a deep past and a future that cannot be timed, only studied, mapped, and prepared for with care.